So today we will revisit actually about deep reinforcement learning. We'll talk about policy gradient algorithm. So let's start from some review on Markov decision process, MDPs. So a set of states that are defined as S and set of actions that are defined in A. The state probability that actually this probability mean that we are in this probability over the state for given take and action. Okay, so discount factor eta is actually how we are believe in the future actions. Okay, so reward function is actually set of the real numbers that are define our rewards of actions that we can do in every state. Okay, so for simplicity, we are talking about discrete numbers. Okay, so it will be discrete rewards, and our MDP is finite. Okay, so it means we have some limit. So about discounting. So the discounting formulation across all episodes that we actually have, it's actually we breaks our episodes for some trials. Okay, and in each trial we can actually change our discount factor. Okay, so example actually we will if we will take the playing breakout. Okay, so each run of the game is an episode. Okay, so every trial is our episode. Okay.
Question. In the last slide, you said we are making the simplifying the assumption that the reward is discrete.
Yeah.
How this assumption is simplifying? What is the difference if the reward is discrete or continuous? Maybe you assume that the reward is deterministic vs stochastic. Maybe how does the assumption that the reward is discrete?
Sorry, 1 minute.
What?
Yeah.
Why do you care if the reward is discrete or continuous?
Okay, the problem with the state of if continuous will be when we actually derive the function. Okay.
Okay.
So for there you will see some assumptions that we are doing here, and
okay.
Here actually from the perspective of if the continuous or discrete for optimizing MDP, it's not very.
Okay.
Right. So. Yeah. Sorry. Okay. So here. So the discount formulation is actually from 0 to 1. Okay. But 1 is actually we believe in our next actions and give them actually gamble on them and give them a big annotation. If we are not believing in our actions, our parameter will be as small as 0. Okay, so it's appropriate for continuous tasks in which the interaction continues without any limit. Okay, so the example of this is actually vacuum cleaner robot. Okay, so it's represent focus on the episodic tasks. Okay, so in each task actually we are playing our game. In each time, each iteration, it's a new game. Okay, there are no some conditions on the game rules for each episode. Okay, so it's independent. They're actually independent episodes. Okay, it's very important for them. Okay, so agent environment interaction. So the agent and environment interact each time of sequence is discrete. Okay, so for actually our time steps they are discrete. Yeah, it's not continuous because it's actually in each time we are actually in new game. Yeah, So where t can be infinite, okay? So of course we're not going to implement it on
Because you are bounded in S and actions, right? So
Yeah.
it will eventually become periodic, right? The
Yeah.
state machine?
yeah, it's the machine. So sure. So at each time our agent receives some representation of the environment, so it actually has a t, and so st in actually is part of s, and use this select and action at. Okay, so actually a action of our st is available actions that given in the state. Okay, so it's all actions. A is all actions that can do in some specific state. Okay, so one step later, this agent, our agent, okay, receives a numerical reward, our numerical reward, all the specific actions, yeah, and finds itself in new state. Okay, so we actually collect our all rewards of the given state, and then we actually go into the next state. Okay. Yeah, also you can ask.
No.
Yeah. If you have, it's actually I have one state, I have state, okay. I have some actions that I can do from in the state, yeah. So actually, I'm doing my actions, yeah. I'm collecting my reward from an MTP, yeah, from the MTP rule, and then actually I'm going to the next state. Till I'm actually ending my game, okay. Great. So at each time step, the agent implements a stochastic policy, or actually mapping from the state to probability of selecting each possible actions. Okay, so the policy is denoted pi t, where pi t is actually probability of taking action A when in the state S. Okay, so the probability to take in some action, okay, it's actually defined as pi A given S. Okay. So if I'm in a specific state, I have all my leaves, okay. Actually, I have some probability to take them, okay. And then I will update this policy. Okay? Each policy define our probability to take some actions, and then I want to maximize my reward, yeah, by giving more probability to sections that give me the better reward in the end, okay. So a policy is a stochastic rule by which the agent selects actions as a function of the states. Okay, so the following learning methods specify how the agent changed its policy using the experience. The experience is actually our episodic games. Okay, great. Okay, so let's start. Now we're actually digging into the mechanism of our actions. So. Action selection, okay? So it's time t, yeah, now the deterministic t, agent tries to select an action to maximize the sum gt of discounted rewards received in the future, okay? So actually, as I told you, it's actually what the future rewards, yeah, in a given time are depends of how I trust for to the next steps, okay? And it's actually defined in these formulas, okay? So it's actually RT plus 1, and then actually I have for the next I have some compensation of actually of ether, yeah. So in the future I actually my compensation is actually small. I trust less and less, yeah. It's actually work like that. Okay. Some questions about GT?
When the sequence is finite, when the time is finite,
yeah.
Sometimes the policy can be dependent also in time.
Yeah.
Okay.
Yeah. So sometimes the policy can be. Sometimes your policy can be. You can define the policy. It be dependent on the sequence. Okay.
Yeah, because the time steps are not symmetric. For example, in the first you see some number of steps ahead, and in the next time step it's not symmetric to the previous time step because you see less.
You're right. In the algorithm of the policy gradient of the games, you have there you have the definition of the types. Okay, here it's actually only your action selection. If in action selection, it's actually every time you have no memories. It's not a recurrent neural network. It's an unmemories. Okay, it's actually feed forward. So it's all time is actually for your playing right from the reset. You have some reset. Okay, so it's each of the states have reset their memory. Okay,
Mm-hmm.
each time you're actually playing the new game. Okay.
Okay.
Great. So before we talked about some selection of the action, yeah. So now we want to actually determine the value function of the action. Yeah, is actually value function. It's actually what my action give me. Yeah, value function. What my reward? What the value function of each node? Okay, I have state, which actually node. Then I need to add to determine his actual value function. Okay, great. So actually, it's not the introduction. So I will give you some if you have no background. So about the first game when you are actually playing, you have no value function of your nodes. Okay, the first time you are doing it, we actually run our value functions are random. Okay. So then we actually it's like learning. We are trying to learn it, okay, by estimation. We are actually we generate some random value function, and then by actually probabilities of actions, we define new value functions, yeah, of each node. And in the end of the process, actually, we actually have the right value function that appropriate to the probability that we define of the probabilities of the if of each leaf. Yeah. Great. So the value q pi actually you have policy. Yeah. So each policy define your actions. Yeah. Because each policy is define what you're going to do in each step. Yeah. So the Q, actually the reward of the policy P, and this in given state S for action is of taking action A in the state S under some policy. Okay. So is defined as the expected return starting from S, taking the action S, and therefore following the policy P. Okay. So you have in each MDP game, you have pi star. What is pi star? Pi star is actually the best policy to that achieve the best reward. Okay, that achieve the best reward for giving it. Okay, and we have assumptions. We have assurance that this policy is existing. Okay. Pi star is existing in every game. In every game we can find by MDP, we can find this pi star. Okay? I remind you this is greedy algorithm. Yeah? So this algorithm is greedy, so he's learning, he's trying some actions, and then he actually, by memory what he did before, he changed for getting better policy. Okay, so we started from some policy, and then we maximize the policy we maximize the reward, and it's actually by maximizing the reward our policy is changed. Okay, till I'm getting to converge to the pi star, and pi star is actually the best policy that I can achieve in each step. Okay, great. So the q pi is the action value function for policy. Yeah. So for given actually. Q pi for SA is our expectation of pi for given GT, where ST is actually S and AT is actually okay. And actually our GT, as you see before, here is explicit form. Yeah, we actually it's our GT. Okay, so it's our GT we defined before. Okay, right? Some questions? Great. So, BELLMAN equation. It's actually, BELLMAN equation is actually our connection to the deep reinforcement learning because it actually gives us some control. Control of what are we going, using our deep learning, we estimate some probabilities, and then we want how we control our reinforcement process, our reinforcement control. Yeah. So, BELLMAN equation is the equation that expresses the relationship between the value of the state S and the value of its successor states. Okay. The value of the next state must be equal the discount value of the expected next state plus the reward expected along the way. Okay, so you have some reward expected along the way, and what you have actually achieved from the last iteration. Okay, great. So the value. Okay, so this is the expected value of R plus the sum of the time discounted rewards, starting over actually we are going for all successors that we have for the states, and all the next rewards are and over all possible actions A in the current state. Okay, so what we actually do, we have all our possibles, we have all our actions that actually we can do in the existing state. Okay, and we take all our rewards from the successor states. Okay, and this we define our BELLMAN equation. Okay. Okay. So let's define some formulas. So optimality. Optimality is actually a policy that is defined to be better than or equal to another policy. Yeah. The expected return is greater than or equal to that of the other policy for all states. Okay? So there is always at least one optimal policy by starting before that is better or equal to our that all other policies. Okay? Then you can actually you have assurance that you have this by start. Okay? All optimal policies share the same optimal state value functions. It's actually V star. Yeah, it's value functions. I remind you, value functions is actually what we defined in our state. It's a value function of each state. Yeah, and which gives the maximum expected return for any state S over all possible policies. Okay, and all optimal policies share the same optimal action value Q, which gives the maximum expected return for any state action pair S A over all possible policies. Okay.
When you speak of expected return, you speak of earlier we spoke of the action value.
Yeah.
Now
Yes.
we speak of the state value.
Yeah. So when I'm speaking about expected return is actually it's actually our reward from all our actions. Okay. Okay. It's all, I'm taking the value function in the existing state and the all rewards that we had before. Okay.
So isn't this the definition of Q?
Yeah. Sure.
But now you say that it's the optimal state value, which was defined differently.
Okay. Again, we are talking about action value function.
Okay, I didn't see the last part.
Yeah. So it's action value function Q. So it's Q star is defined like this. So for Q star, the value function that you have.
Okay.
Yeah. Again, you.
Okay. Yeah.
The value function. Okay. For the Q star, you have this. You actually all optimal policies share the same optimal action value. Okay. Action value is actually the value of your specific norm, of your specific state. Okay.
Yes, and the state value function is a function of Q and pi. So given pi and Q, you get
Sure.
the same thing.
Okay, it's it's a bit false. So it's you can see you can as the point of view. So here my point of view of it's from values. Okay, you have the policy that achieves these values. Yeah, this is the Q star. Okay, but again, the Q star you for every policy you achieve the Q star. Okay, so there are some Q star for every policy. It's not means that this is we are actually looking for the pi star eventually, yeah, because the pi star will give us eventually the maximum reward for all policies, yeah, among all policies. Here it's actually some only for specific policy, the Q star. Great. Okay. So now we talked about the MTP and about the actions and the value functions. Let's start to talk about policy gradient methods. Actually, we will talk only about ACTOR-CRITIC method. You have Monte Carlo method, but actually, it's if you want, I will explain a little bit how they works, but no, we are not going to deep explanation about them. And we have some reason because ACTOR-CRITIC is actually the best policy gradient methods that achieve the best results in the less complexity that we have. So actually, what actually policy gradient methods? Okay, it's a very good question. So it's actually run your policies for a while, yeah. See what actions led to highest reward, and increase the probability for this action. Okay, so we have some actions, and then actually the action that leads for the better reward, then they actually will have better. We are increasing their probability, and then we actually give them more priority. Okay, so it's policy gradient methods. Okay, so. So what we did before, we learned the value of actions and then select the actions based on the estimated action values, yeah? Then the policy was generated directly from the value. Now we want to learn a parameterized policy, yeah? Actually our learning process, yeah, it's the deep reinforcement learning. Now it's actually, we'll take in account. So a parameterized policy that can select actions without consulting a value function, okay? The parameters of the policy are called policy weights, okay? This is our policy, this is our weight. So a value function may be used to learn the policy weight, but this is not required for action selection, okay? So policy gradient methods are methods that for learning policy weights using the gradient of some performance measure with respect to the policy weights, okay? So, and then we want actually our methods will seek to maximize performance. So the policy weights are updated using the gradients. Okay, we will update our weighted, and then by their updating, we will actually increase our reward. Okay, so this is what we will learn. Okay, so policy-based reinforcement learning, some definitions. Search directly from the optimal policy pi star. Okay, we can use any parametric supervised machine learning model to learn policies. Okay, actually, the policies pi a given s. Okay, and our vector theta. It's theta. Yeah? Theta. Yeah, I always say. So where theta represents the learned parameters. Okay, so and then we actually after we learn it by some deep learning algorithm or the deep learning algorithm actually we will learn the probabilities of each state, yeah, or regression. We can actually learn the specific algorithm, the specific values, yeah, of our theta, and then we will recall the optimal policy. Is the policy that achieve maximum future return. Okay, great. So actually, we will this is actually continuous one. Yeah, because we are talking about generate probabilities. Yeah. So we actually have we have two options to learn the policy. one we have actually continuous, and then we have discrete. Okay, we have two options. But we will learn probabilities. So we will because we learn to learn probabilities, we actually using by a continuous definition of our policy. Okay. The second method, why you should ask me why we are not going to learn discrete policies, and the answer will be, what do you think? Why I prefer to learn continuous probabilities? Yeah, anyone else? Why?
What do you mean continuous probability?
Okay, so it's a good question. So look, here I will use deep learning algorithm to predict our probability A given S. Okay? So
But A is discrete, right?
A
is discrete.
Yeah.
So your probability distribution for choosing an action is discrete. You have a probability number for each action given a state. And when you sample it, you're sampling a discrete probability distribution.
No. I will sample from continuous probability. I will sample from continuous probability to you're right. My S is discrete. Yeah.
No, your A. I mean your
Yeah,
A.
my action is discrete. Yeah. But probability to choose probability to choose it will be continuous. I'm not using to. I can use the other option is to use discrete.
How do you represent the distribution?
How we
Can you
present?
show like an example of typical values for A and how the distribution of it can work? Distribution.
Okay, so
I know when you're doing a reinforcement learning such as this with continuous actions, then you have a continuous probability. You have a Gaussian distribution with a mean somewhere, and then you sample it. But when you have discrete actions, I don't understand how you have a continuous distribution.
No, you're right. I forgot to give some assumption. I will use continuous sections.
Okay, so I asked previously.
No, you're right. I forgot to mention it. It was introduction about MDP. So now we actually have two options, or to using action and the states that are actually from discrete domain, and then our probability will be discrete, or using continuous. Sorry, I actually have some slides that I forget. I did some. I forgot. Actually, here we do switch, and why we do this switch? Because it's actually better to learn. Yeah, continuous values. Yeah, because it's actually learning. These algorithms are more stable. Okay, using learning by policy learning. Continuous probability are more it's more stable. Okay.
When your problem is continuous, such
Yeah.
as control.
Yeah.
But when you're playing Atari games, you don't have continuous actions.
No, when you play guitar games, you have you need to use Actually,
you still use policy gradient, but
you still use policy. Yeah, you have okay. So we have two options here. We can use we can use the discrete option where our action and states are defined discrete, and we have option where we can use the continuous probability. We prefer to do it because the algorithm is working better. Okay, so great. Now we actually talked about this issue. Great. So policy weighted vector. So our policy weighted vector theta. Yes, it's our notation. The policy pi is actually which represents the probability that the action A is taken in the state S with the policy weighted vector. Okay. If using learning, so if you will use the value function weight vector W, performance measure and eta of it's actually eta of theta. Okay. It's eta or nu. It's nu, eta, theta, no?
Theta.
Eta theta, yeah. It's eta of theta, yeah. So we have actually our episodic case, yeah? Our episodic case, remind you, we have episodes, we learned about episode. So our episodic case is actually eta theta. So it's actually our value of policy in given a zero state. Okay? So actually our performance is defined as the value of the start state under the parameterized policy. Okay? So we actually have our, let's talk about algorithm. We actually have some initial state, yeah, and we need to actually to define some initial state, and it actually define our eta theta, and then we are going to optimize during the level. Okay, great. So policy approximation, yeah. Actually, we are talking about deep reinforcement learning. So we are deep learning is actually genius approximator, yeah. But let's add some now we will add some magic, some voodoo, because before we actually talked about some definitions of mathematics. So from now we will start to actually to add some voodoo for the process, but it's all defined. This is the fun, no? The policy that can be parameterized in any way so that we can provide our probability actually a given C and for a action in a given state is the differentiable with respect to its weights. Okay? Because we have weights, our weights is actually our theta vector, yeah? So we can actually differential, so it's differentiable with their respect. Okay, so if so, we will change our weights there, and then we will actually react on our policies. Great. So to ensure exploration, we generally require that the policy never becomes deterministic. Yeah, and so by
what you're showing here is a discrete distribution.
Yeah, can you repeat? I didn't heard your first.
But the last equation on the slide is an example of a discrete distribution of overactions. You're taking the softmax.
Yeah, it's discrete because you
No,
sum over
yeah,
the-
here is discrete distribution. Yeah.
But previously you said we're now talking about continuous distributions.
Well,
Okay, you're right. Maybe I sent you
These
some
lines.
lines here. Yeah.
When we talked about it, we said
Maybe I did some.
you said a continuous distribution over continuous actions, but now you're showing us discrete distribution over discrete actions.
Yeah, you're right. Okay, you're right. No, he's right because the expectation. This is actually the.
It's written in the third bullet from the top. Discrete and finite set of actions.
Yeah. So no. As by notation, okay. So we need to. Okay. So this is so. Let's actually let's revisit it. Okay. So let's talk about discrete distribution. Okay. We're talking about playing game. Playing game. Okay. So
if it's not discrete, so you can just replace the
sure.
summation by
It's not a
one.
problem.
It doesn't-
Yeah, sure. It's not really. Or yeah, it's not really a gift. So. Okay, so so assume the discrete and the finite state of our actions. Okay, so form parameterized numerical preference. Okay, so actually we have some age that depends on actually our vector theta. Okay, so for each state action pair, we can use a deep neural network. Okay, so as policy approximator. Okay, so here we will approximate our policy by neural network, and then we will use the softmax. Okay, that the most preferred actions in each state are given the highest probability of being selected. So our reward, actually our pi, will be well. Okay, so it will be actually expectation of some age that defined actually on selected pair of state and action, and we actually normalize it on all expectations of all, summing all actions that we have. Okay? Yeah. So you're asking why I can actually remove the expectation?
It's
Excellent, sorry.
You can.
Yes, because you're choosing the maximal value of age, right? You choose A such that age is maximum. So
Yes.
and softmax doesn't change that. Doesn't change the A you will choose.
But you're trying to sample a distribution.
Yeah.
Softmax give you a distribution over.
Softmax gives you distribution of the.
If you're taking always the one with the maximum score, then you're deterministic.
Okay.
You could define it, I don't know, you define some H tilde by log of H and then, yeah, just
No. Yeah, so the right answer is because you're sampling. Yeah, it's not it's you're sampling from some distribution. Like you know you give our softmax is actually we have the distribution probability. So you can actually only to take it from you need to sample it and not only to choose it. Okay. Great. So here actually we take is actually our probability is will be actually taking the given policy and actually dividing by all summing all samples. Okay. Is it clear? Okay. Okay. So this is actually three methods of how we can update our gradient mechanism. Actually, how to learn. Yeah, and we will talk about ACTOR-CRITIC policy gradient. The others is actually more. It's a finite difference policy gradient. Is actually you will need a lot of computation. There are a lot of you will need a lot of computation to do it. And Monte Carlo approximator, it's a good approximator, but actual policy is actually empirically give better results. Okay, and ACTOR-CRITIC is give you more control because we have actually here two nets. Actually, we have here two learnable phases. Okay. And we will talk about it. But again, if you're interested, you can find more information about first two methods. Okay. So ACTOR-CRITIC. Actually, the methods that can learn approximation of both policy and the Bell functions are called ACTOR-CRITIC methods. Okay, it's actually a set of methods that we have actually we have our actor. So our actor is actually he refers for our learning policy. So he dictates about the policy that we are learning. Okay, and we have critic. Critic refers for our value function, which is usually actually our A-state value function. Yeah. So first actor is actually choose our policy. Yeah, and then actually critic gives him value function according to the policy. Okay, so this is actually in this way we will learn because one of them actually control the policy and the other actually collect estimation of the value. Okay, great. So the critic is actually bootstrapped. Okay. So the state values are evaluated using the estimated state value of subsequent states. So the number of the steps of the critic methods controls the degree of our bootstrapping. Okay. So the degree of the bootstrapping is depends on the number of the steps that ACTOR-CRITIC methods do. Okay. So actually, it's all about you need to declare to define one-step ACTOR-CRITIC update, and then you will do it iteratively. Yeah. So on policy method, the state value function update the rule, LTD0, update rule. Okay, the policy function update the rule is shown below. So it's actually we have our actually theta t plus 1. It's actually the next weight updating rule. I remember you. It's actually our weight update rule. Yeah, like we did like we have in our data science and deep learning. Yeah. So actually theta in time step t is actually plus some constant alpha, and gt minus value function of in the current state, and we're actually doing our gradient according, okay, our policy. We have gradient that optimize actually our gradient that actually optimize theta according to the value function. Okay. So we will need to define, and we will do it about it a little bit later. We need to define this minus. Okay, what is actually this brackets? We will define what they mean. It's called advantage. We will define it. Okay. So here, yeah. 1 minute. I will actually what we actually do here. Here is actually it's explicitly form of GT. 1. So if you remember, you can trust me. It's actually GT in 1. It's actually RT plus 1 plus actually our value function of discounted value function of the next. Okay. Yeah.
So GT is the estimation for the value function.
Yeah.
Okay.
It is estimation. Any questions? Okay, great. Okay, so one step of an ACTOR-CRITIC algorithm is actually we have here some flow. So we have our input A, differential policy parameterization. It's actually our probability you see before, yeah, and we have our actions that from all the actions and states from all the states, and that are actually vector that our learning weighted vector, and we have our input differential state value parameterization V, yeah. So and our parameter step size. So we define that alpha and beta are larger than 0. Okay. So what we do? We initialize our policy weights data. We have some like in deep learning we have some initialization algorithms. Yeah, and the most famous is actually randomized. Yeah. So or you have some more specific initializations, but I think that most of them converge to randomize. So it's not a big deal. And then we actually initialize our policy weights, weight theta, and the state value weights W. We repeat forever. Yeah. But forever, we repeat forever our initialization S for state of episode. Then actually we have one that goes to I, while S, our state, is not terminal. What is terminal, guys? The end of the episode. Yes. The terminal defines actually the end of the episode. Again, let's revisit it. So actually, we are learning on each episode. We have episodes, yeah. So each episode must have start and end. So terminal is end, and then we are going to the next.
Usually when doing policy gradient methods, don't we sample multiple episodes simultaneously to increase the
You're right.
variance?
The next slides. Yes, you're right. The best algorithm is asynchronous, parallel.
No, I'm not talking about whether it's synchronous or asynchronous, just
No, the best.
so when you do update to the parameters, it's with a larger variance of samples.
You're right. What it remembers from the deep learning? No, it's not remembering something from deep learning. The learning, it's not remembering something.
You need IID data.
Yeah, sure. So it's actually this kind of learning gives us better generalization. Yeah, like we're doing in a batch. Yeah, so it's what I expected. Batch. When you're doing, why we're using batch, guys? Because we want to generalize our that algorithm will learn from on more samples. Okay, so yeah, you're right. Next slide will show. Next slide is actually A3C algorithm that it takes this algorithm and makes it. Okay. Okay. So while this is not terminal, we will actually set our A is approximately the probability of a given state. Okay, and we actually take action A, absorb from assessors as tilde, okay, and then we actually doing here updates. Okay, so here we actually update our weights, and by updating our weights, we are updating our parameter theta. Okay, when we did it, we actually our I is actually will be I discount. Yeah, next one, and S tilde will be S. Okay, and if S tilde is the terminal, then our value function will be 0 because we need value function of the state that actually the terminal 0. It's actually we end it, and then we doing it again. Okay, some questions about one step of critical grid?
This is each of the updates of W theta is a gradient descent step.
Yeah,
And so
ascent.
gradient ascent step.
Okay, and so our function our not loss function, our opposite of loss function is R plus gamma V minus V squared. Is delta squared?
I didn't understand it.
I'm trying to understand what is the return we're maximizing. So it looks like it might be delta squared, but I'm not sure. That's why I'm asking.
What criteria of your
What is our anti-loss function? Our reward function.
you want okay. So you want actually to maximize your reward. Okay. So for given you are not sitting it's here, not explicitly here. You want to maximize your advantage, and we.
But lots of stuff, you have two ones, right? You have one for the critic,
Yeah.
which is the value function. What is it called?
Again,
It's a state value.
Yeah,
State
one
value
wants to maximize the reward, the actor.
yeah.
And
I want
critics.
eventually I want to maximize my reward from the given policy. Okay, it's
Okay.
there.
And the update step includes a gradient of this reward, right?
Yeah,
So I'm asking, what is this reward? That's the question.
you ask here what they're trying to maximize it.
Yes.
So actually I want to maximize the advantage. Okay. The advantage is actually I have an explanation in the next step. It's actually the loss function is actually I want to maximize my Q. Okay.
From an implementation point of view, when I want to implement something like this in, say, PyTorch,
Yeah.
I implement a loss function and then I backpropagate through it. The loss function in this case is the log of the policy
Yes. In this case, it's
with no target.
with no part.
Maybe this was what you meant?
Yeah, it's not. You want actually in the finals you want to your loss function is the log of all policies. Actually, you have an example in the site. I gave you some example of ACTOR-CRITIC implementation of PyTorch.
But when you update the value network, you don't need a target because the value network you update it in a supervised fashion using data that you generated with the episode.
Here.
Now this is the
Again. When I did what?
W, the
Yeah,
the
what is the
critic
W?
network. Sorry, the critic network.
Actually,
The critic.
The critical. Okay.
So there's like the gradient of V.
Asynchronous methods actually work better. So when you use asynchronous gradient assembly to optimize controllers, it's actually very useful for deep learning algorithms that controllers are deep neural networks, which take a long time to train. Yeah. So asynchronous gradient descent speeds up our learning process, and we can we can use multi-core GPUs, CPUs to train it. Actually, work as it worked before. Actually, we divide our data to few devices. Okay, so parallelism works. Parallelism algorithm. So asynchronous execute multiple agents in parallel on multiple instances of environments. Okay, so this parallelism decorates the agent data into more stationary process. Since any given time step, the agent will be experiences a variety of different states. Okay, so actually using asynchronous actor learners, our agents, yeah, we can think about as each actor learner is a thread, yeah, because we actually have taken our learners and we actually multiply the threads, and then they will update regarding the policy. And that's what you asked about, yeah, before. So run everything on the single. Okay, so the run on single multi-core CPU to avoid communication costs of sending irradiant parameters, but you can you have new hardware like DMAs. You can do it very fast, transferring your data among CPUs. So multiple actor learners running in parallel likely to be exploring different parts of the environment. Yeah. And we can explicitly use different exploration policies in each actor level to maximize our diversity. Okay? By running different exploration policies, do you familiar what is exploration is? I didn't ask before. Yeah, exploration is like the way you change your values of the actions. Okay, so you actually can define my exploration will be all time adding some parameters. Yeah, or I can actually to start from some initial state, and my exploration I will my next step will be far away to try all regions. Actually, I have some surface. Yeah, and I can actually explore this. Yeah, I have some surface. This is my surface. Yeah, this is my surface. This surface has actually all kind of action that I can do, and you can actually start. We actually start with somewhere here. Yeah, and then we can do it like this way. Yeah, this is one of the ways of expression, and the other way you can actually start here, and the next step will be here. The next one will be here. You can look at like in gradient surface that you have a lot of minimas. Yeah. So in some way some problems you actually don't want to actually to do it continuously, or actually doing try all options. You want actually to try more different options, okay? Some more options that actually are existing on the opposite, very far from your previous options, okay? Some example actually, if I want to find some, if I know that if I want to find we talked about compression. So if I want to find out my best bit allocation on each of layers, each layers actually can be represented as in his size. Okay, so I can start actually from some explore. This will be my first options that I can give actually that all my layers are represented in a floating point. And the next exploration I can try is actually one by one. It's actually it's far away, yeah. And I'm not increasing one by one, and I'm going all some far options, basically. Okay, so I can define that my next step will be 31, 31, 31, 31. It's actually, or I can actually define some more domain exploration. Okay, so is the way how actually how I cover my situation, my all options. Okay, great. So the different exploration process in each actor learner is by maximizing the diversity. Okay, so here we no need to reply for reply memory. We instead rely our parallel actors employing different exploration policy to perform the established role undertaken by experience replay. Okay, so this is deep Q learning. We are not talking about him. Since we are no longer rely on the experience replay for stability learning, we are able to use on policy reinforcement learning methods to train neural network in stable way. Okay, so it's an exploration used for given each thread. Different exploration policy helps improve robustness. As I said, generally improves performance through the better exploration. And you will be using epsilon greedy exploration, which is epsilon periodically sampled from some distribution by each thread. Okay, it's actually some sample. We are not doing it this way as I talked before, like manually, but we are using some sampling of this epsilon. It's give more stochastic. It's מוסיף stochastic ומשפר מאוד את הדברים. Okay, so A3C, okay, is actually the parallel ACTOR-CRITIC algorithm. We are maintaining our policy, our function, okay, and estimate of the value functions VST, okay. Then N is actually step ACTOR-CRITIC method. As we value-based methods use parallel actor learners and accumulate updates to improve technical stabilities. In practice, the policy approximation and the value function share some parameters. Okay, so we use the neural network that has one softmax output for the policy, given policy, and one linear output for the value function. As it's actually our estimation. Yeah, this is what we estimate with all non-output parameters shared. Okay, now we actually define the advantage definition. So our advantage definition is actually defined like A, okay, and for given A and S, this is actually Q of this state minus V. And V, this is our value function. That we actually how we estimate the V. We are executing actually neural network that estimate our V's functions. Okay, so this is actually what we estimate during our deep learning algorithm. We are approximate our V, and then we actually we know our Q, and Q minus V is actually what we define our advantage of our given state. Okay, so the quantity are our reward. Yeah, I remember it's our reward minus our value function that we estimated from we run our algorithm and we estimate is an estimation of the advantage. Okay.
The advantage you show down there below is the same as TD error, right?
Yeah.
So this is a k-step TD error.
Yes. Yes, you're right. This is case TD error. The advantage estimate for k-steps. ACTOR-CRITIC method is shown. Okay, so this is actually our algorithm. we have some, okay, let's go through. So we have some, we assume some global shared parameters, okay, and we assume some thread specifics. Our threads actually are, every thread will have some exploration or policy, what actually about instruction. We reset our gradients, synchronize thread-specific parameters, yeah, and we actually perform our one-step function, yeah. So this is our algorithm, but each thread have other exploration that he actually find our reward, okay, and update the actors about the policy, and then actor actually find other policy, define other policy, and the actors estimate our value functions, our reward.
Where do you see the exploration part? The different explorations?
It's threads. We defined that each thread assumes thread-specific parameters vectors, and actually it's our threads. Yeah. So it's thread. Actually, what is status? Yeah. It's actually the when we estimate our reward. Yeah. We are actually updating our status. Yeah. So for given points. But each of threads, actually the advantage of this algorithm that because we have a lot of threads that estimating for the given policy the reward, we can use other for each of them other exploration. Okay. So some summary. So get faster training because of parallelism. We can use on-policy reinforcement learning methods. The diversity in exploration can lead to better performance than the synchronous methods. Yeah? And in practice, the on-policy A3 algorithm appears to be the best performing asynchronous reinforcement learning methods in terms of performance training speed. סיימנו את הקטע באנגלית, זה כבר מוקלט, האם יש לכם, אני מתנצל שזה קורה באנגלית, פשוט אני יודע שאתם עדיפים בעברית.